Hello and welcome once again to Captain Goodspeed Maths. I'm Joe, if you're new around here, and today we are going to be discussing definite integrals. So the learning objective is to understand how to use integration to find the area under a curve. So just a little side note, I do apologise for not having all of the videos out yet. I appreciate the FSMQ is soon if you're watching this when it comes out. All of the lessons will be out in time for that. I've had my last ever university exams, which are kind of a bit more important than this, so that's why they haven't been out, but they will be out before the exam, so don't worry about that. And I will be doing lessons on logs and recurrence relationships, that sort of thing. They're all going to be later in the course. So today we're going to do definite integrals. So without further ado, let's get into things regarding those. So integration, we talked about this last time in the other video that was on integration. So if you don't know how to integrate, make sure you go back a lesson on the playlist and refresh yourself with that. But essentially integration is the opposite of differentiation, so if you can differentiate, you can be confident that you can integrate too. Just remember the constant of integration. So to integrate a piece of algebra, we basically add 1 to the power and divide by the new power and add a constant c. So there you go. Don't forget the c. That is just a recap of what we did last time out. So remember that c fella that we were adding? Well, sometimes you're asked to work out what it is, and we did that in the last lesson. But sometimes we have things called limits on our integrals, little numbers on the integral sign, and it looks a little bit like this. So there you can see the limits are -2 and 2, so that says to me calculate the integral between -2 and 2 of x cubed dx. So this time we can be a bit more sloppy with our c. So the bigger number will always be on top at this level anyway, and at any level I don't think I've ever come across an integral where it's the opposite way around, but hey ho. This is used to find the area underneath the curve. So what we're doing is putting up 2 big goalposts at 2 and -2 and shading the area in between. So let's have a little look. So there you go. There's your graph, x cubed, and we're putting up a big goalpost at -2 and putting up a big goalpost at 2. And we're trying to find this little area here, which is shaded in yellow. And that is exactly what we're finding, i.e. the area under the curve. Or between the curve and the x-axis, I should really say, because you can be pedantic and say, oh well, that's not the area under the curve, it's over the curve. But hey ho. So there you go, the integral between a and b of f dash of x, which is just another way of saying dy dx if you remember the differentiation lesson. Dx is equal to f of x put between the limits of b and a. So we're obviously going to have to find out what f of x is through integration, so which equals f of b minus f of a. So those b and a are the limits of integration. We have the integrating with respect to x as we had in the last lesson, and basically what we do is we integrate, then put b and a through and subtract them off each other. So that's exactly what we need to do. So here's example 1 then. Evaluate the integral between 2 and 4 of x squared minus 2x with respect to x. So think about the graph. So we draw the little graph there. So x squared minus 2x, that actually factorizes to x brackets x minus 2, so we know we've got intersection points at x equals 0 and at x equals positive 2, and we draw a little curve through it, and we know that it's well, we don't know its lower limit actually. Its lower limit possibly, I'm trying to think about this. No, it's just a parabola. Yes, just think of it like that, Joe. Don't confuse yourself. Anyway, so we put up our goalposts between 2 and 4 because those are our limits. Apologies for knocking the mic there. Because those are our limits, 2 and 4. So we put up 2 big goalposts and we want the area in between. So it's like, okay, it's a little bit of a rough guideline, but essentially the area between the curve and the x-axis. So that's the area that we are calculating when we do this. So what do? We integrate and then put the top limit through and subtract putting through the bottom limit. So here we go, we integrate first, so add 1 to the power, divide by the new power, so we get x cubed over 3 minus 2x squared over 2. Now remember that c fella that I was talking about before, so imagine that we were putting a plus c into this, and you'll see that when we subtract them off each other, we're going to get a plus c and we're going to get a minus plus c. So these c's will just cancel away eventually when we do the sum. So let's just erase all the ink off this side because I've got a funny feeling it's going to come up next to it. It didn't actually, but there you go. We put our limits through, we put 4 through, and we put 2 through and subtract them off each other. So be very, very careful of double negatives here. So we get 4 cubed over 3 minus 4 squared minus 2 cubed over 3 minus 2 squared. Very careful of double negatives, and we get 6 2/3. But it's area, so we need units. Doesn't tell us the units in this question, so we call it 6 2/3 units squared. So that's what you would say if it asked you for the area. I mean, if we're being pedantic about it, if it said evaluate that, then we don't really need this unit squared. But if it says calculate the area, then make sure you put a unit squared on there, or centimetre squared, or whatever, if it tells you the units in the question. So 6 2/3 is the answer there. Easy peasy. On to 2 then. So this is the same integral that we had in the sort of premise of this lesson. So the integral between minus 2 and 2 of x cubed with respect to x. So once again, we draw our graph and put up our goalposts at 2 and minus 2. And what do you notice about those areas? Well, they're symmetrical. So that'll come into it a little bit. One is above the axis and one is below the axis. So they're going to cancel each other out basically when you do the calculation. If you just put minus 2 and 2 through the integral of that, because it's an even function when you integrate it, you will just end up with the same answer taken off each other, and it'll be 0. So what we're going to have to do is do it one stage at a time and basically add the numerical value of the area together. So we put an artificial goalpost down the middle of it, where basically the line of symmetry, and it happens to be at 0, 0 this time. So we now split the integrals into 2. So we've got the integral between 2 and 0 of x cubed, and the integral between 0 and minus 2 of x cubed, both with respect to x. And we do the usual process. We integrate first. We get x to the 4 over 4. Now what I mean by that being an even function is that no matter what number you put into x to the 4 over 4, you're going to end up with a positive answer. So if you put minus 1 through, you're going to get the same answer as 1. If you put minus 3 through, you're going to get the same answer as putting 3 through. If you put minus 100 in, you're going to get the same answer as you put 100 in. So basically f of minus x is equal to f of x. So if you want to think of it like that. But essentially, back to what we're doing, we put the 2 through, we put the 0 through, and we take them off each other. So we get 4 there. Similarly, we'll do it for the other functions. So we integrate x cubed and get x to the 4 over 4. We put a 0 through, we put a minus 2 through. Remember, 0 is bigger than minus 2. We put the 0 in first, then subtract by putting the minus 2 in. So we get minus 4. Now then, think about the area. You can't have negative area. Area is just a number. It is a thing you can count, the thing you can hold. It is not negative. So we just take that 4 and we'll add them together. So we subtract the answers. I guess 4 minus 4 is 8, but it's area, so we need some units, so we get 8 units. Now that is a very tough question, and that's probably the sort of higher sort of tariff questions on the paper, but it's all about practice. So what you want to do in the exam, a key idea is to draw this graph, because if you didn't draw that graph on here, you'd probably lunge into just calculating that normally, get 0, be happy, move on. But think about your answers logically. Is it logical for there to be 0 area? between these two graphs. If you draw it, you can see there's definitely not no area. You've just got symmetrical graphs. So we're going to have to split the integrals and take the numerical answer, which is 4 in each case, and add them together, and it's going to be 8. So hopefully you found that helpful. That's where we're going to leave it for today. It's quite a tricky concept to get your head around, but it is all about practice. Make sure you know how to draw basic graphs like x cubed and x squared minus 2x, whatever. You know, just to get a simple answer. Put up your goalposts, shade in what area you want. It's the area between the curve and the x-axis that you want. If you have found it helpful, make sure you leave a like down below. If not, then let me know down in the comments what I can do to explain it a bit better. Remember, all of these lessons are also uploaded to the Google Drive, so you can go through them at your own pace, and you can also check the playlist for the rest of the FSMQ course. I've also got the old Spec on the channel, so a lot of the concepts from that are still in the course, so if you can't wait to watch the rest of the course, then make sure you head over to the old playlist. But thank you very much for watching. Subscribe for more FSMQ videos, and very best of luck with your exam.